Okay, good everyone. Um, Now we'll be looking at heat sink for semiconductor devices. All right. Now, what is this heat sink? What's a heat sink? Remember, a heat sink is actually an electronic device that is made of good thermal conducting material. So they are usually attached to our a transistor or any power electronic power electronic semiconductor devices or a microchip to dissipate unwanted heat. So the heat sink is used to cool the circuit component, by dissipating the excess heat to prevent any overheating or failure of that circuit or microchip or transistor or thyristor or IGBT. Okay, and this will help to improve the reliability and performance of the circuit. Let me just show you an example. If you check here, this is a typical example of a heat sink. So this is heat sink, or this one. If you look at this, it's a typical heat sink which is used to dissipate excess heat from the microchip. And we have this also. All right, it's a heat sink. And this is also a heat sink. All right. So now, what we have here is just a schematic, all right, to show the sections of the heat sink. Let's say this is our transistor, or thyristor, or IGBT, or microchip, all right, and this generates heat. Remember, it's a switch. Transistor is a switch. As the thing is switching on and off, all right, there's always heat being generated, and we need to dissipate the heat. So that is why we need a heat sink. So when you mount this on this, the heat sink has a case. Okay, it has a case, and then it has the heat sink itself. So this is a case. This is mounted on that, and then so heat that is generated here is going to dissipate, flow through here until it comes out. This is the ambient outside. Okay, so we have three sections. The junction between the transistor or the microchip and the case, and from the case to the heat sink, and from the heat sink to the ambient. So as the heat flows, okay, there's going to be some resistances against the flow of the heat. So there will be a resistance here in this case. There will be a resistance here, all right, and there will be a resistance when this is coming out. All right, so that's why we can sketch this, okay, with this just like our normal electric circuit, but this is, in this case, is a dissipation of heat. All right, so if heat is generated here, all right, the heat has to dissipate. It means that at this junction, all right, this is the junction between the transistor or the microchip and the case. So there's going to be a temperature there, which you can measure. If you touch it there, at least you feel it. That temperature at that point is what we call the junction temperature, TJ. All right, so between that junction temperature, okay, and the case, so as this flows here, there's going to be a resistance against the flow. That resistance is RJC, which is the resistance between that junction and the case itself. Okay, so as the heat goes out, that will have the resistance there between the junction and the case. Now, if I now measure the temperature at the case, NETC, right inside, you touch the case, you are going to feel it, feel something. That's the temperature, TC. Okay? And then as the heat continues to flow, it crosses, gets into the sink. All right? The sink, because of the material of the sink, it might still hinder or try to resist the flow of that heat being dissipated. So there will be a resistance between the case and the heat sink. All right? And then across, after that, the temperature, if I touch this point, let's say here, I'll get a temperature TS, which is the sink temperature. And then between that sink temperature and outside, the heat has to dissipate from here to out, right? So there must be a resistance. There must be a hindrance to that. And that is resistance between the heat sink and the ambient, outside, the ambient temperature. All right? So now this is now the temperature outside. So it means that heat has to flow from this point of high heat through this down to the ambient, to outside. All right? So we can easily take the power here, just like current flowing. So we take this power dissipation, total power being dissipated from the transistor as the current. All right, that's why we have to put this as if the current source. So as current flows through here, all right, we know that, I'm just saying current, we know that current I, I is V over R, right? Or V is IR. So if I take this I as current, in other words, PT, which is the power being dissipated, okay, you consider it like a current flowing. All right? Now it means I can replace this like PT, right? And then this is still your resistance. And that resistance is actually a thermal resistance. It's not electric resistance. It's resistance against the flow of heat. So it's a thermal resistance. So this is thermal resistance between the junction and the case. This is thermal resistance between the case and the sink. And this is thermal resistance between the sink and the ambient, and the outside, ambient temperature. Okay? So it means that this P, if I take it as a current, multiply by the thermal resistance, then that will give us something that looks like a voltage. But in this case now, this is the temperature difference. So temperature difference between this point and that point is like your difference in voltage. Okay? So temperature difference here. Temperature difference. Let's say temperature. So temperature difference, right? It's like a difference in voltage. It's like voltage difference in voltage. Okay? While the power dissipated there is like current flowing. And the thermal resistance is like normal resistance. So if I say V equals to IR, it means I can also put the difference in temperature, Tj, T junction, minus TA, okay, now equal to PT into RJC plus RCS plus RSA. So that's how we got that. So you should know that formula very well. Okay? Because we'll use that to solve problems. All right? Did you get that? Thank you.